Welcome to Down the Rabbit Hole with Eric Ebersol.
Imagine dropping a weight onto a spring and watching it wobble, slow, and then settle. Every tick of that motion is a tiny computation in progress.
Welcome to Down the Rabbit Hole. I'm your host, and today we're tracing how simple, touchable devices make core computation ideas feel obvious.
That spring image, it's immediate. You can almost hear the metal sigh. So what's the plan? Show us a few little setups and then let us tinker?
Exactly. A quick tour. One mechanical integrator to make state visible, a passive RC filter to reveal timescales, and an op-amp summer to feel weighted addition. Each one is a small experiment you can do in an evening.
Let's start at the workbench. Picture a coil spring with a tiny mass on the end. Drop it and watch. The mass bobs up and down, each swing carrying memory of the push. In computational terms, that's integration. The position reflects the accumulation of past forces over time. It's a live state you can point at.
I'm with you on the poetry, but I'm also thinking like a teacher. Some folks will ask, can that scale? Can you build a curriculum around springs?
Good push. I'm not saying springs replace equations. I'm saying they complement them. Let me be concrete. Measure the settling time with 3 different masses and plot it. You'll see a clear trend. It's empirical evidence, not just metaphor.
I'm not sure I buy complement without seeing how students respond. Do they really connect the plot to the math, or do they just enjoy the toy?
Fair. In my classes, I ask students to predict, increase the mass, will the settling time get longer or shorter? They predict wrong at first, then run the test and revise the mental model. That hypothesis test loop is the pedagogy. You get data, you update a model.
Okay, that helps. So the experiment isn't just spectacle. It's a mechanics-backed way to exercise scientific thinking. I like that.
Next, move to electricals, an RC network. Hook a resistor and capacitor together, feed a sharp pulse, and watch the edges soften. Think of the capacitor as a little bucket that fills and leaks.
You can literally see that on an oscilloscope, or even judge it with an LED's brightness. Swap in a larger capacitor, and the LED lingers longer. The system chooses what details survive.
Right, and here's a teaching trick. Feed a noisy square wave and have groups predict which resistor or capacitor change will clean it up fastest. When the signal smooths into a calm curve, students stop asking why the math matters. The math has a face.
That phrasing, math has a face, that's the hook. But don't forget trade-offs. Increase smoothing and you lose responsiveness. Beginners often chase perfect smoothing and miss the cost.
Guilty as charged. Okay, last core rig, op-amp summers. Plug a couple of input resistors into the negative input of an op-amp, and the output is a weighted sum of those voltages. It's addition in hardware.
Hold on. Weighted sums? Physically? Say more about how you feel a resistor's weight in an experiment.
Easy demo. 2 identical input voltages into equal resistors give equal contributions. Swap one resistor to a higher value and the output shifts. Students can measure output change with a multimeter and watch the weight change numerically. Resistors become knobs for influence.
And add a diode clip or a soft nonlinearity, and you start to approximate a neuron's behavior. It's surprising how little you need to build an analog neuron that behaves recognizably.
Let's make this an evening project you can actually finish. Build 3 small demos. A spring mass toy for integration, an RC smoothing circuit with an LED, and a breadboard op-amp summer. Parts list. Cheap spring and washers for mass, a small breadboard, resistors, a selection of 1K, 10K, 47K, 100K, capacitors in the nanofarad to microfarad range, an LM358 or similar dual op-amp, a 5 to 9 volt battery or bench supply, jumper wires, a 555 timer or microcontroller for pulses, an LED and current limiting resistor.
Safety first. Keep voltages low. Double-check polarity on capacitors and op-amps, and wear eye protection if springs might ping.
and teach students to change one variable at a time. It's the fastest route to insight.
Assembly tips. Mark the spring's rest point. Time several oscillations with your phone and log settling times. For RC, drive the circuit with a 555 generated square and swap resistors to watch LED behavior change. For the op-amp, start with 2 equal resistors so students trust the math. Then change a resistor.
Expect quick wins. Add mass and the spring takes longer to settle. Increase capacitance and pulses linger. Change a resistor and the op-amp output shifts predictably. Those tactile moments cement abstract terms, state, time constant, weight, into real experience.
Before we sign off, 3 takeaways. 1. Accumulation is physical. Mass and inertia give you memory. 2. Filtering is about timescales. Resistors and capacitors decide which details survive. 3. Weighted sums are everywhere. Resistors and op-amps let you build simple linear models you can touch and tweak.
And a teaching tip. Set prediction checkpoints. Ask learners to write a one-line hypothesis. Run the test, then compare. That practice builds the same model-building habits used in digital design and machine learning.
We'll link schematics, a simple parts list, and classroom prompts in the show notes so you can jump straight in. Try one experiment tonight. Take a photo, note your data, and see how fast the abstraction becomes concrete.
Subscribe for more short, practical peeks into surprising corners of computing and teaching. We'll keep the project small and the insights big. Don't be afraid to learn.
Thanks for listening to Down the Rabbit Hole. Subscribe, try an experiment, and tell us what you found. We may feature your photo or data in a future episode. That is an interesting topic. See you next time.
You've been listening to Down the Rabbit Hole with Eric Ebersol.